Welcome back. Today we're going to be looking at Venturi meters. But before we dive straight into Venturi meters, let's go back a step to what we did in pipeline flow, where we looked at Bernoulli's equation, where, as you'll remember, we had energy after an event was the same as the energy before that event plus any losses along the way. Now, the event I'm talking about in pipeline terms could be fluid flowing from an area where the diameter is, let's say, large, down to an area where the diameter is smaller. And between those two places, the sum of the energies would have to be the same at the 2 points. Now, let's just start off by saying that there's no change in height between the 2 points, meaning that we are left with those two adding up to a number and those two adding up to the same number. So if you were to play with the velocity between the two places, and let's say you were to make this velocity less than this one, to make it balance, this would have to go up. So to achieve balance, if this one goes down, this one must go up, and the same on this side. Okay, let's keep that in mind. And go straight back to this situation here, where we have what's effectively a pipeline reducing in diameter at this point over here. Now, we all know that if a pipeline reduces, from the continuity of flow equations we learned earlier, Q equals VA, it follows that here at 2 the velocity must be greater than at 1. So if we go back to Bernoulli, if we make the velocity greater at the second point, it follows that to get the equation to balance, this term here, which is pressure, must in fact reduce. So to summarize, if we have a reducing pipeline such as this situation here, the area that sees the high velocity of flow will have lower pressure. And we in the Venturi meter use that to our advantage by putting tappings into the pipeline at this point before the reduction, and then another tapping at the reduction, where we've now just learned the pressure will be less. If we attach a manometer to those 2 points, and let's make it a clear glass tube or plastic tube, it doesn't matter as long as we can see through it, and let's put some sort of gauge fluid in that manometer that we've created, and note the difference in levels whilst there is flow happening. We can immediately use this as a meter for measuring flow rate, and that's what a Venturi meter does. So let's just read through these words here. It says Venturi meters are a useful way of measuring flow in a pipeline. Typically, a gauge fluid such as mercury is used in the limbs of a manometer and connected as shown. Remember, we make the gauge fluid a heavier fluid than that which is in the pipeline, and one that does not mix readily with the fluid in the pipeline. So mercury would certainly fit the bill for that, but you could use other liquids in the manometer. But let's for now stick with mercury. In this example, flow is from left to right, so that is how the Venturi meter works. You'll note that it has a smooth reduction down to the neck and then a very gradual increase again, so as to minimize any forms of shock losses through the meter. The pressure in the neck of the meter at 2 will be lower than in the pipeline 1. We've discussed that. And then this causes the difference in level X in the gauge fluid as shown. Now, using Bernoulli's equation, this formula for a Venturi meter has been derived, and we can do that, but for the purpose of the course that you are enrolled for, we are going to simply apply the formula. Now, the formula is one in which we can work out discharge, Q, given the dimension X, the all-important dimension X that we're going to measure from the meter, and a few other variables that we are going to discuss. Here they are laid out for you. Q is the flow rate in the pipeline. That's the answer that we want to get in cubic meters per second. Coefficient of discharge, that is capital C subscript D, is a coefficient of discharge for the particular Venturi meter. So a Venturi meter would be tested, and then it would be labeled with a certain coefficient of discharge. And that, if you look at the formula, is a factor to ensure that your final answer is in fact true and it allows for any errors that there are in the meter. We'll discuss how we get to that in a moment. M is a ratio of correction of areas, area 1 over area 2. Now obviously this is round, so it would be pi over 4 d squared, whatever the diameter is at 1, upon pi over 4 d squared for this diameter over here. That would give you m, and m fits into the formula over there. We've discussed what the two A's are. Obviously they're in square meters. Then specific weight, remember that's measured in newtons per cubic meter. Very important number in fluid mechanics. That is the specific weight of the gauge fluid. The M is probably because we use mercury a lot, but of course this need not be mercury. So it is simply the specific weight of whatever you're using for your gauge fluid. And then omega is the specific weight of the pipeline fluid. And actual discharge over theoretical discharge is therefore the coefficient of discharge. So let's dive straight into an example. A Venturi meter tapers from 300 millimeter diameter to 100 millimeter diameter in the neck. The coefficient of discharge for the meter is 0.98. You'll see it's very close to 1, but they are factoring it to allow for the losses in the meter. A mercury manometer is connected between the tapping points at the two diameters above. The fluid in the pipeline is water, and there is water in contact with the mercury in both limbs of the manometer. So in other words, there's no air trapped or anything like that. If the difference in mercury level is 55 millimeters, that sounds like X, calculate the flow rate in the pipeline. Let's start off by working out M, which is the ratio of the two areas. And we know area is pi over 4 d squared. So in fact what we have is pi over 4 d1 squared upon pi over 4 d2 squared. And we can immediately see that the pi over 4's can cancel, and we are simply left with d1 squared over d2 squared. Now I've said to you all the way through we must use base SI units, so in fact we should have 0.3 squared over 0.1 squared. But you'll see over here I've just left the two values in millimeters, which is not a base SI unit, but being a ratio this would yield exactly the same answer as that. But if you're more comfortable with using base SI units, feel free to do so. And of course that gives you an answer of 9 for M. On to the rest of the formula. Actual discharge is equal to CD times area 1 over square root M squared minus 1 multiplied by the square root of 2gx, and in brackets specific weight gauge fluid over specific weight pipeline fluid minus 1 close brackets. So that's what we're aiming to use. So we have 0.98, that's your CD, pi over 4 times 300 times 10 to the minus 3, that is 300 millimeters expressed as meters squared, over square root of m squared, which would come out to 81 minus 1, square root 2gx, obviously the 55 millimeters expressed in meters, over specific weight of gauge fluid, it being mercury, it's 13.6 times heavier than water. Water's specific weight is 9810. The SG of mercury is 13.6. And below the line is the specific weight of water, 9810, minus 1 close bracket. Work all that out and you get an actual discharge for our meter of 0.0285 cubic meters per second. Now here's a slight variation on the theme. This is also a Venturi meter, but it doesn't have any gauge fluid in it. And the way they handle this is the actual liquid in the pipeline enters what is effectively a manometer on its own on the one side, and the liquid in the pipeline at the neck enters another manometer. And then here where the two manometers connect, we pump in air pressure until we get this surface between the air and the liquid to be in a convenient range, somewhere in this area, so we can actually see it. And once we pump in enough air pressure to get that to be in the correct position, we then shut this off with a valve, and then we can use the manometer as before by just measuring this dimension X. But we didn't have to source any mercury or any other gauge fluid. So it's a very versatile way of constructing a Venturi meter. So there's exactly what I explained moments ago in a problem. It says, in an experiment conducted in the fluids lab, a Venturi meter was set up as per the sketch below. The water in the meter was allowed to enter two tubes arranged as separate manometers. There's the one and there's the other one. To allow for a variety of flow rates, air pressure can be introduced into the tubes as shown at above or below atmospheric pressure. So that's at this point here. This is then shut off. So once you've introduced the air pressure, you then shut it off. And the difference in height between the limbs is then used to calculate flow. Right, there are two forms of formula that we're going to use for Venturi meters. Here was the one we've discussed so far, and that is the one we use when we have the traditional meter with a gauge fluid in the manometer. Okay, so that one you already have, but there is another one. If you simply know the difference in pressure between the two tapping points, 1 and 2, and you actually know those values as P1 and P2, you can use this formula over here. So I want you to note this one down. It's actually a simpler formula, and as I said, it is the one you use if you don't have a manometer, you don't have gauge fluid, but you do know the difference in pressure between the two tapping points. Okay, so back to our modified Venturi meter that we discussed moments ago. Here it is over here, and we've set it up, and we have introduced our air pressure, and we have the surface of separation over here and over here. What if we could set up an equation that compared these two pressures based on dimension X? Then we could use the formula I've just mentioned moments ago. Well, two sections back we did look at fluids at rest, and we looked at manometers, and we looked at pressure in a fluid. And if you cast your minds back, you'll remember that we considered, for example, PA, the pressure at this level, being equal to the pressure at 1 plus the specific weight of the liquid that you're in multiplied by the extra depth that you went to. So in other words, the pressure here is greater than the pressure here by specific weight of the liquid you're dealing with times the extra depth that you go down in the liquid. So PA would be P1 plus specific weight times dimension Y. And then remember that same liquid, same level. PA was the same as PB because it is the same liquid at those 2 points. And you could therefore say that PB over here is equal to P1, which was the pressure right up here in the pipeline, plus specific weight times dimension Y. Now if you go to the other side, pressure at D, that's down here, is equal to the pressure at 2 plus the specific weight of the very same liquid times dimension Y plus X. Now note that this dimension is Y, which was this one here, plus this little piece X. But pressure at C equals pressure at D, so therefore you can say that pressure at C is in fact equal to pressure at 2 plus specific weight times Y plus X. But if we neglect the weight of air, which is very small in comparison to the liquid that's likely to be in the pipeline, so we're not going to look at the difference in pressure between, let's say, this level and this level in the air. So we would say that it's the same at B, or in fact we'll say the air pressure is the same all the way through here because there would be negligible change because air is so much lighter than the liquids we're dealing with. So we could safely say that pressure at B must be equal to pressure at C to make this manometer balance. and then we can go up and find what pressure B was equal to. There it is there. We could go up and find what pressure C was equal to. There it is there. And we could equate the two. We could move P1 and P2 to the left-hand side of the equal sign, and we could move the rest to the right-hand side. And we could move things around a bit and ultimately end up with X being equal to P1 minus P2 over specific weight. And that's important to us because, remember, we had this new formula. Let's see if we can use it. There it is there. We now actually have this term thanks to us knowing X. So we can put it into this equation and hopefully find Q, which is what we're looking for. So let's use some numbers to make it more meaningful by means of an example. Let's say a Venturi meter as above, in other words exactly the device we've been speaking about, has diameters of 50 and 25 millimeters and yields a dimension X of 50 millimeters whilst 1500 liters per hour of liquid is flowing through it. That sounds like the actual rate of discharge. We must calculate its coefficient of discharge. Right, so we have X 50 millimeters, we have the two diameters. Knowing the two diameters, we can immediately find that ratio M. And we also know that P1 minus P2 over specific weight is in fact 0.05 meters. Because remember, we figured out that that's what X turned out to be. And we put it into our new formula and we find that the theoretical discharge turns out to be 0.502 times 10 to the minus 3 cubic meters per second. Remember, if the formula does not have a CD in it, it is theoretical. So here we have the theoretical discharge at 0.502 liters per second. And we were told that in fact the flow was 1500. So coefficient of discharge, remember, is always actual discharge over theoretical discharge. So working in liters per hour, which are not base SI units, but it doesn't matter because it's just a ratio after all, we can put the one over the other and find that the coefficient of discharge for this particular Venturi meter is 0.83. Now here's an actual lab experiment. And we have a very similar situation, so we're just repeating what we've done, but by means of this example, let's see if we can work it out. It says in the setup described above, so it's that very same type of Venturi meter, the following actual readings were observed with a Venturi meter having an inlet size of 55 diameter and a throat of 38 diameter. And we were told the actual flow rate at 10,000 liters per hour yielded an X value of 430 millimeters. Then 7,000, 205, 3,046, and we must find the coefficient of discharge for each reading. So I'd suggest you stop the video at this point and see if you can work out these three coefficients of discharge before continuing. Right, there's diameter 1 at 55 millimeters and diameter 2 was 38 millimeters, so M turned out to be that. Area 1 we can work out, pi over 4 d squared, and then applying it to the formula for theoretical discharge, we find that the theoretical discharge is 3.7492 times 10 to the minus 3 cubic meters per second, but the actual discharge we'd already worked out. We converted the liters per hour to cubic meters per second, and we found 2.777 times 10 to the minus 3. Then we remember that coefficient of discharge is actual over theoretical. So our Venturi meter has a coefficient of discharge of 0.74 when we are at this situation, 10,000 liters per hour, 430 millimeters X. Then at the next reading, it came out to 0.75, and for the last reading it came out at 0.68. So this particular Venturi meter was fairly similar, but it did have a slightly different coefficient of discharge when we got to the lower flow rates. And if you were to plot the coefficient of discharge for a typical Venturi meter like this, Under experimental conditions you might find a curve that looked a little bit like that, and this is in fact the lab practical, the way it's conducted.